Howdy, folks. Here we go again. We are going to take a look at equilibrium. So, you're probably asking yourself, what's equilibrium? Well, I'm glad you asked. Equilibrium is the point at which the rate of the forward reaction equals the rate of the reverse reaction. So reactions can go forwards and backwards. Yes, they absolutely can. Okay. Take water for example. If you were to synthesize water, H2 plus O2, stick them together, and you have H2O. You can do a reverse reaction in which you decompose that water molecule that you just made. So now you've got H2O. You decompose it into H2 and O2, and now you've got a reverse reaction. Okay, so when you have a reaction and it's the forward reaction rate equals the reverse reaction rate, that is when you reach equilibrium. Okay, now every reaction also is going to have what's called an equilibrium constant. So let's take this particular reaction right here. Okay, I've got my reactants, I've got a double arrow, meaning that it's a reversible reaction, and then I've got my products over here as well. Now, in order to determine our equilibrium constant, what I'm going to do is I'm going to say that K sub EQ, which is indeed my equilibrium constant, K sub EQ is going to equal the concentration of the products raised to whatever its coefficient is. So you remember the mole road and all that stuff, the number of moles was the coefficient, okay? So you're going to take the concentration of the product raised to its coefficient, okay, times the other product raised to its coefficient over the reactants to their coefficients, okay? Now that probably seems pretty cray-cray, but if we take a look at at this little example here, I think it's going to make it a lot easier. So here's what we've got happening. I've got my equilibrium constant. I don't know why that little keyboard keeps popping up. It just really wants to cover it. Okay, there we go. I've got my equilibrium constant here, and I notice that my products are C and D, specifically 2C and 4D. So therefore, what I'm going to have is K sub EQ equals the concentration of C raised to whatever the coefficient is. So in this case, 2 times the concentration of D raised to the fourth power, okay, just like it is right here, over my reactants, okay, the concentration of A squared times the concentration of B cubed. Now, when we do that math, we are going to get a value for K. Okay, now depending on what that value is, let's say that the value for K is between 0 and 1. Okay, now you're never going to have a K value less than 1, but let's say that you're going to have a value between 0 and 1. We're going to say that the equilibrium lies on the left-hand side, or reactants are favored. Okay, if the K value is greater than 1, that means that equilibrium rises to the right, or our products are favored. Okay, now here's a good way to remember that. Let's say we've got a number line, okay, and I've got 0 right here on my number line, okay, and then on my number line I'm going to continue on over until I get to 1, okay, and then I'm going to continue on from there into infinity, okay? So this is increasing the normal way that a number line should. So anything between 0 and 1 is going to lie on the reactants side. Anything 1 and greater is going to lie on the product side. That's how I like to remember it, okay? Now, the only time that you include your reactants and products is when they are aqueous or when they're gases. The reason for that is because only aqueous things and only gaseous things can have concentrations. You can't have a concentration of a solid, you can't have a concentration of a liquid, therefore you may not include them in our equilibrium constant. If you have a solid or a liquid, you just leave it out, okay? You just pretend like it does not exist. Well, what about the units, Mr. Coder? Don't put units, okay? Just leave it as K. So here we go. If I were to write a K sub EQ expression for each of these, that I would do that as follows, okay? I'm going to say that K sub EQ. Now, sometimes you will see KSP or KW. If it's got a K, that's it. That's what you're looking for, okay? So my K sub EQ equals, for this particular reaction, equals my products. I've got carbon monoxide. It's a gas, so it can be included. So I'm going to do the concentration of carbon monoxide to the what power? It's assumed that there's a 1 out front, so it's to the first power. Times my other product, which is H2. Can it be included? Yes, it can, because it's a gas. Its coefficient is 3, so it is to the third power. Next, I've got H2O. It's a gas. It can be included. Okay, that's going to be to the first power since its coefficient is 1. And lastly, I've got CH4 to the first power. It's a gas. It can be included. And that is how we do the K sub EQ expression. Okay. Let's do one more, just so we can. Okay, we'll do the K sub EQ of this one right down here. Okay, so I'm gonna do K sub EQ. Remember, you can call it KW if it's still in water, KSP, whatever. If it's got a K, it's good. For this one, my product is HI. It's a gas. It can be included. Okay, that's HI to the second power because my coefficient is 2. Over H2 is a gas. It can be included. So I'm going to put H2. No coefficient, so it's just going to get to the 1. Now notice I2 is a solid. Solids cannot have a concentration, so therefore we are not going to include it. So this right here ends up being my equilibrium formula. Okay, now let's go ahead and translate this into a problem. It says the following reaction reaches its equilibrium state. N2F4, which is a gas, yields 2NF2, which is also a gas. At equilibrium at a temperature of 25 degrees Celsius, the concentration of N2F4 is found to be this, and the concentration of NF2 is found to be this. Calculate the equilibrium constant of the reaction. Okay, so we can do this. We can do, we know that K sub EQ equals my product, which is NF2. It's a gas, so it can be included. NF2 squared, because I've got a 2 right here, over my concentration of N2F4. It's a gas, so I can include it. N2F4 to the first power. Now, I can actually calculate the K sub EQ of this because I have concentrations here. My concentration of NF2 is 1.131. 1.131 times 10 to the negative third power. And we're going to raise that to the second power. Divided by N2F4, 0.9989. 0.9989. Okay? And so now I'm just going to do this math. So I get 1.131 second E negative 3. And I'm going to square that bad boy. And I get 1.279 times 10 to the negative 6 divided by 0.9989 equals 1.28 times 10 to the negative 6 is my K sub EQ. Now, if that is my K sub EQ, then I know that reactants must be favored because 1.28 times 10 to the negative 6 is between 0 and 1. If it were greater than 1, then I would say that my products are favored. Since it's less than 1, I will say that my reactants are favored. But Mr. Coder, what unit do we put? Remember, if you go back a little bit in the notes, you'll see that we do not include a unit. We just call it 1.28 times 10 to the negative 6 equals K sub EQ, and that is it. Here's what I would like for you to do right now. I want you to try this problem right here. Okay, give it a whirl-ski, see what you can figure out, and we will talk about it next class. Have a day.